For number 25, you're actually asked to work out this integral of x minus inverse tangent of x all over x to the third dx. It's important for you to note that no matter what method you try to work this integral out by hand, you wouldn't be successful. You could try to, do integration by parts. You could use every method that we've covered so far in class, and you'd be frustrated for sure. How can we actually move to many other problems that would be very difficult or even impossible to do by hand? The answer is with series. I mentioned before that you can use as a statement of fact, actually even by memorizing this, that inverse tangent, if you look at its expansion, you're going to see odd powers. Everywhere where you're looking, you're going to see x is raised to an odd power. An odd expression would be 2n plus 1. You're going to have the same denominator, whatever exponent you have up on top, that same number is going to be down below. Of course, this is going to be changing from a plus to a minus, but we could very easily write this out with sigma as well. And we could say we're going from n equals 0. We'll have negative 1 raised up to the n, x, and I forgot that negative 1 to the n here up in my nth term. I just want to correct that too. But this nth term, really want to tell you over and over again, this is so critical, that the nth term that you see in the term by term expansion, you can put inside of sigma. Well, why are we even starting off with that? Well, I think you can see we've got inverse tangent of x. You might wonder, though, you might think, well, wait a minute, it's technically a minus inverse tangent of x. Yeah, you could put a negative there. You would change every single sign when you do that. In other words, every term would be multiplied by negative 1. What's negative 1 to the n times negative 1? Well, that would be negative 1 to the n plus 1. So my nth term would actually change to negative 1 to the n plus 1. That's something that you could quickly work out. You can see it's virtually the same expansion. You just have changed the sign of every single term, but it looks amazingly close. So where are we going with this? Well, if we keep looking at the integral, you're going to notice that actually we now have that x out in front. It's like we're adding an x to that, so I could just add an x out in front here. And very quickly you can see what's about to happen. Your x and your negative x out in front are going to get canceled out. Now, if you're really on your toes, you're going to say, now wait a minute, that means that I've officially lost my first term. You can see what has just happened here. The x and the minus x are going to cancel out. So losing that first term, we've talked about that in terms of derivatives. Even though we haven't taken a derivative here, we could say, look, this is equivalent really to have lost that very first term. And you can quickly see as you expand this, again, I keep mentioning that you can check your sigma by plugging in your n equals 1 here, and you could see that you generate exactly what you're looking for. But again, this is all well and good. We've just dealt with the numerator of that integral. You're going to notice, of course, we're dividing by x to the third. So how do we fix this up? Well, we can quickly say, well, if we're dividing by x to the third, what that honestly means is every single term here is divided by x to the third. Everywhere. Including what we have over here. So if I'm dividing by x to the third, you'd actually wind up with just 1/3. Here, you're losing 2 x's. You'll have x squared all over a 5. Here, we're losing 3 x's. You'll have x to the 4th all over 7. And even as we move inside of sigma here, or to our nth term, I should say, if I'm going to lose 3 terms, you can see I'm going to write all the way up here in the top right corner. If we had x to the 2n plus 1 divided by x to the 3rd, really that's saying subtract those powers. And you can see that the 1 and the minus 3, you'll be left with 2n minus 2. So we'll have 2n minus 2. We'd still have the same denominator of 2n plus 1. You can think, oh my goodness, what's going on here? Well, now, even inside of sigma, you're going to have the same thing as that nth term. You'll have 2n minus 2. Wow. Can still generate sigma by starting at n equals 1. You can more or less see that you're still going to work everything out. But where are we going with this? This is not the end. It's not just saying we'd like to, stop right here. Rather, there's an integral out in front. We're really being asked to integrate all of this. You can think, well, my gosh, how's that going to look? Well, we're getting to the very end of the problem here. We can say now we finally have what has been asked for. We've got this integral. An integral that would have been impossible for us to do by hand. What is this thing? Well, do the reverse power rule everywhere. We'd have 1/3 with an x. Here we'll have x to the 3rd all over 5 times a 3. Notice I didn't turn it into 15. Here I'll have x to the 5th. Down below I've got 7 times a 5. And you can keep going here and say, well, this would be -1 to the n plus 1. I'm going to bump up my power by 1. I'll get 2n minus a 1. If I add 1 to -2, I'll be right here. I still have my 2n plus 1 down below, but now I have 2n minus 1. And by the way, as we integrate our sigma, we'll still start with n equals 1. You can see that we're going to now have this x to the 2n minus 1. Down below we'll have 2n plus 1 times 2n minus 1. And guys, right now you have a power series representation for that integral. You can double check by using your sigma. Double check that it does in fact generate what you're looking for. You'll see quickly that it does. And one more thing that I need to tell you, one little subtle thing that we forgot. You're going to have to put in a plus C everywhere. If you check the back of the book, you're going to see the author puts in a plus C. Probably puts that, plus C out in front, perhaps. But talking about checking the back of the book, the author would probably say C plus, and here we go. You'll say, wait a minute, I'm looking at the back here. I'm not seeing exactly what we've written down. More than likely, the author has started the counter back at n equals 0. And that means everywhere where we've got an n, we've got to counterbalance. If I lowered my counter by 1, I'm going to increase my power, every n expression by 1. This will now become n plus 2. A little bit of work here. If you look at this 2n minus 1, imagine that I gave you 2n plus 1 minus 1. That would be 2n plus 2 minus 1. That would become 2n plus 1. So you can see what's happening. Another way to look at it, 2n minus 1 is an odd number. Go to the next odd number. Down below, if you use similar logic, the next odd number after 2n plus 1 would be 2n plus 3. We already saw 2n minus 1 went to 2n plus 1. How would we change 2n plus 1? Well, very much the same way. If you wanted to see that worked out exactly, it'd be 2n plus 2 plus 1. You could see that's how we'd get our 2n plus 3. But so critical for us to realize this is an equivalent form. You could let n equal 0. You should see that at the 0th term, we start with negative 1 squared. We'd get x to the first. Down below, we'll have 3 times 1. If you let n equal 1, you'd get your next term, this negative x cubed, all over 5 times 3. So I leave that to you to quickly confirm.